As you already know, a bit is the smallest unit of information processed by a computer. It's letter. When we speak, we combine more than 20 letters to express ideas, but a computer only needs 2. You can call them whatever you want, up and down, black and white, dead and alive, or for practical reasons, we use 0 and 1. And bits are not something abstract. We can realize them in real systems. Anything that can take 2 values works as a bit. Practical examples include putting a ball in one shelf or another, a dot or a line on a paper, or allowing the pass of an electric current or not. So what's the big deal about the bit? Well, after the discovery of the strange quantum world, physicists have discovered that there might be a unit of information which would work better for certain things. The idea came about by considering what would happen to a bit if it followed the rules of quantum mechanics. A quantum bit, a qubit. And what makes these quantum rules special? First, the number of states a qubit can be in increases quite a bit. It is no longer limited to 0 and 1. It can be a superposition of both, a mix of both states in any proportion. In this representation, the higher the arrow points, the more relevant the 0 state will be, and the lower the arrow points, the more relevant the 1 state will be. Easy, right? Well, no, because combinations can also be negative. Literally, there might exist a 0 minus 1 state. But there's more, because the coefficients of these combinations can also be figured using complex numbers, which infinitely increases the possible configurations of a qubit. All these states can be observed with the Bloch sphere. And just like before, currently we can find physical systems that behave like qubits. For example, the polarization of a photon, the spin of a particle, the position of an atom trapped in a double well potential, or the state of an electron inside an atom. But hey, easy. Don't get overwhelmed with complex and negative combinations. In this sphere, we still follow the rule we mentioned. The higher the arrow points at, the more important the 0 state will be, and vice versa for the 1 state. Keep that in mind. However, although a qubit can be found in infinite different superpositions, observing all of them may be hard. In a qubit, the only thing you'll end up measuring is its 0 or 1 state. In the quantum world, measuring means perturbing the initial state and making the qubit align with the vertical axis. It is this alignment or projection that we end up observing. Now, will it align pointing upwards, which means measuring the 0 state, or downwards, which will correspond to the 1 state? If we have 100 equal qubits and measure them in the same way, we will find that randomly sometimes we will obtain 0 and sometimes 1. But there is a pattern. If we look at the number of times 0 and 1 appear, it turns out to be related to the orientation of the arrow. The higher the arrow points, the more times we will have 0 appearing, and the lower the arrow points, the more times we will have 1 appearing. Does it ring a bell? The more relevant one of the states in the superposition is, the more probable it will be when measuring. More precisely, the exact probability of measuring each state is the square module of the coefficient that accompanies it. But as before, don't get messed up with this. The important thing is, the higher, the more probable it is to measure 0. In fact, if the arrow is completely vertical, in the 0 state, you will always observe 0 when measuring it. And the same goes for the 1 state. In these 2 cases, the qubit behaves like a classical bit. But if the arrow points at a different direction, the result will be completely random and unpredictable, even if you have the probabilities. This random behavior, the fact that we cannot predict what will come out, doesn't come from a lack of information about qubits or from not having good theories or precise measuring tools. It's something intrinsic to the quantum world. Due to its nature, the state of the qubit is not determined in 0 nor in 1. It's an undefined property. But when we measure and force it to give a value, the qubit changes, projecting itself in the axis, and the superposition where it was is lost. Measuring in the quantum world has severe consequences. Hang on, because it gets weirder. So far, we have been focusing in one axis with the Bloch sphere, the vertical axis, which physicists usually call the z-axis. This axis was our reference setting, which one is 0 state and another is 1 state. But we could use another axis for our measurements, the horizontal or x-axis, for instance. Just like before, when we forced the qubit to project in 0 or in 1, by measuring the x-axis, we are forcing it to project in the state that points right or the one that points left. The more the arrow points right, the more probable it will be that you will observe the qubit there when measuring it. And the vice versa for an arrow pointing left. In terms of 0 and 1, the right state corresponds to the equitable addition of 0 and 1, and the left state to the equitable subtraction of 0 and 1. And this has consequences. Imagine we depart from any state which we don't know and decide to measure first in x and then in z in order to try to clarify it. What we are going to obtain in the first place is a horizontal state, right, for instance, and now from there we'll measure in z. However, as the right state is a perfect mix of 0 and 1, the possibilities of measuring in z and projecting one or the other are the same, 50-50. Once we have measured in x, we won't be able to obtain more information about the initial state, no matter how many other axes we measure in. But this is not x-axis's fault. Check this out. In terms of right and left, the 0 state is the equitable addition of right and left, whereas the 1 state is the equitative subtraction of right and left. This implies that if we measure z first and then x, instead of doing it the other way around, we will have the same problem. The state will project along the z-axis. Let's imagine the result is 1. And as we've seen, we are in front of a perfect mix of left and right. It's 50-50 once again. Besides, the final state at which we arrive measuring first in x and then in z is not equal to the one we get at when measuring first in z and then in x. This is one of the most dangerous things about quantum physics. Suddenly, the order of the factors does change the product. This is precisely the seed from where a famous principle rises. Think of an arrow that is very near the 0 state. This means that if I perform a measurement in z, it's very likely to end up obtaining 0. I am pretty certain that it will happen. But if I measure it in the x-axis, the odds of obtaining left or right are the same. So my uncertainty about the result is almost complete. The qubit gains definition in z by losing it in x. This is Heisenberg's famous uncertainty principle, and we've got there just through one qubit. As you can see, qubits and classical bits are radically different. Let's sum it up. For starters, to begin with, a classical bit can only be in 2 states, whereas the qubit can be in infinitely many states. And the value of a classical bit is perfectly determined before I measure it, while the value of a qubit is undetermined before observation. Moreover, measuring does not affect the state of a classical bit, but measuring the state of a qubit means destroying it. And finally, in a classical bit, you can only measure the 0 or 1 value, that is, the z-axis, but you can measure infinite axis in a qubit, although you have to be careful with the order you measure in. All these differences are what makes a qubit so interesting when you think about stocking, processing, and transferring information. In fact, qubits are already being used to create the most secure communications in the world. But we'll talk about that in a future video. And if you want more science, you just have to subscribe. And thanks for watching us.